Okay, so we just discussed how to determine the order of the reaction for specific reactants, right? So we're going to do one more to kind of carry us in, because now we're going to introduce time, right, and see how that works. So here we have a reaction of sucrose reacting with water to produce fructose and glucose, right? Okay, so here we have three concentrations at their rates. Now, you need to remember, guys, and I didn't go over this in the last video. These are three different experiments, right? So what this is telling you is that one experiment has an initial concentration of 0.10. The second experiment has a reaction or a concentration at 0.20, and then the other one has an initial concentration of 0.50. Okay, so it's not like the reaction is going from 0.10 to 0.20. It's not actually increasing, right? I wanted to make sure that I explained that, but these are three different experiments where the initial concentrations are starting off at this amounts. Okay, now what we're seeing here is in the first experiment, right, we have an initial concentration of 0.10. Second experiment, we have a initial concentration of 0.20. And then as a result, we see a change in the rate of reaction. Okay, so here's what we're looking at. Okay, so we're going to compare these two, and we can clearly see that there is a doubling in the initial concentration between experiment 1 and experiment 2. As a result, we see that if we take reaction or experiment 1 or experiment A and experiment B, and we take A divided by B, we see that we also see a doubling in the reaction rate. So what that tells me is that if I have a doubling in the initial concentration and I see a doubling in the rate of the reaction, then the order of the reaction must be a 1, right? Because it's a 1-to-1. So if I was to write the rate for this reaction, right, it would be K. Rate is equal to K times the concentration of sucrose, okay, raised to the 1. Now, if I was solving this to find the rate constant, right, then the rate constant, the rate constant would be rate of the reaction divided by the initial concentration of the reaction to the first order. Okay, so that's what that means. I just want to make sure that that was clear. Okay, now let's take a look. Let's go ahead and solve for the rate constant of this reaction. I'm going to pick just the first one here, or we can pick the second one. It doesn't matter. Let's go ahead and do 1.23 times 10 to the negative 4, right? That's our rate. Now this is going to be in moles per liters minus 1 times seconds minus 1. Then we're going to divide that by the rate here, which is 0.20. Okay, that's going to be to the first order. And again, remember that this is moles per liters minus 1. Okay, so that's going to cancel here. That's going to cancel here. If I take these two numbers and I divide them, I'm going to end up with 6.15 times 10 to the negative 4. Okay, seconds 1. So my K is going to be equal to this. Okay, all right, so again, just review, right? We've already done this. This is again just going over it one more time. Now we're gonna take this same problem and we're gonna apply it, because now we're gonna introduce time. So what we just realized was that this reaction was in the first order in terms of the reactant sucrose, right? So because this is a first order reaction, we're gonna introduce how time works, right? So let's say you wanted to figure out, how long it takes for the concentration of sucrose to drop from 0.20 to say something else. Let's say 0.10, right? That's going to decrease, because remember, these reactants are being consumed, so the initial concentration of the reactants should decrease, right? Okay, so if this is a first order reaction, which we've already established, right, then our formula is going to look like this. The ln of, the initial concentration over the concentration after a certain time, or time t, is going to equal kt. Okay, initial concentration naught, or A naught, is going to be equal to, of course, the initial concentration of the reaction, right? Initial concentration of the reactant in the reaction. The A sub T is going to equal the concentration time t, right? And then, of course, t is going to be equal to time and seconds. Okay, so let's say we have a question that says, how long would it take for the concentration to go from 0.20 to 0.10, right? Let's say we want to measure the amount of time that it's going to take for that reaction to get down to this concentration from this starting concentration, right? So at this point, we know our starting concentration is going to be 0.20. We want to know what the concentration is going to be at a certain time. So we're going to know that at a certain time, our concentration is going to decrease to 0.10, right? And we're looking for this amount, okay? So at this point, it's just a matter of knowing how to use the formula and plug things in. So if ln of A naught over AT, and I'm going to divide both sides, both of that by K, that should give me the amount of time that it takes for this reaction to happen, right? So let's go ahead and plug everything in, right? So I'm going to take the natural log of 0.20 divided by 0.10. Then I'm going to divide all of that by my K, which is 6.15 times 10 to the negative 4. Okay, so let's simplify this. Natural log of 0.20 divided by 0.10, that's going to give me 0.6931. Okay, then I'm going to divide that by 6.15 times 10 to the negative 4. So t is going to give me 1127.07 seconds, right? So what this calculation tells you, right, is that after this many seconds, the concentration of the sucrose is going to decrease from 0.20 to 0.110, right? And it takes this amount of time, okay? It's pretty straightforward. You just have to know what values go where and how to manipulate your reaction, okay? Let's say instead of looking for time, you're looking for this concentration, right, after a certain amount of time. Well, you're not going to have to do the math for this. So in this equation, this one should also be in your formula chart, right? You're going to look at the equation and just going to rewrite it. Is equal, so the concentration after time t is going to equal to the initial concentration times E, because remember, that's the base to the natural log. And then you're going to plug it in for this, right? So let's use the same example. And let's see if we can figure out after, what, 1,000 seconds? Let's do 1,000 seconds, right? So I want to figure out what my concentration is going to be after 1,000 seconds. So right here, right, all we're going to do then is plug everything in at time t. So our initial concentration, we'll start with the same one, which is 0.20, right? Then we're going to take e to the negative. Remember that our k is 6.15 times 10 to the negative 4. And then we're going to multiply that by 1,000 seconds, right? Okay, so let's go ahead and begin to simplify this process. So if I take e to the negative 0.20, I'm going to end up with 0.5412. If I multiply that by 0.20, I'm going to end up with 0.108 is equal to concentration after 1,000 seconds. So if you look, right, I wanted to use a number that was close to our original, right? So the answer for the first one ended up being 1,100 seconds, right? So at 1,000 seconds, you can see that the concentration is pretty close to what we see up here, right? Because the difference in seconds is not that much. It's a really straightforward equation. Again, you just have to know how to use it and how to plug stuff in. So that's going to be for first order reactions. If your reaction, right, if you find out that your reaction is to the second order, right? So let's say that your rate is equal to K, and the reaction is to the second order, which is what we went over, then the formula changes a little bit. It just becomes 1 over the concentration initial, right? I'm sorry, over the concentration at time t minus 1 over the concentration initial, and that's going to equal your KT. So if you go through this process here, right, and you realize that the reaction is to the second order, then you would simply just use this equation, right? It's pretty much the same process. You just have to plug in and replace values as you have them listed. I don't want to make the video too long, so I'm just going to leave this reaction here, but you are going to see that on your equation sheet. And just know that it's going to depend which formula you use depending on the order, right? Which is why the first video was so long, because I wanted to make sure that you guys understood how to find those reaction orders. Okay, so the last thing we're going to talk about in the video here is going to be half-lives. If you guys want me to do a problem using a second order reaction equation, just shoot me a message and I'll make one for you. The half-life reaction is pretty simple, right? The half-life of a reaction is equal to the ln of 2 over the reaction constant. Okay, so what is this talking about? What is a half-life? So let's say I have a reaction, right, that happens over a course of X amount of time, right? Let's call it days. And my curve looks like this, right? Now, our initial reaction, our initial concentration is going to be here. This is going to be our initial concentration, right? And basically what a half-life is just saying the amount of time that it takes for half of the concentration, right, to dissipate. So halfway down, let's call it here, right, that's going to be half of our initial concentration. Okay, and then if we take half of that, that's going to be about here. That's going to be 1/4 of our initial concentration, right? And if we take half of that, that's going to be about 1/8 of our initial concentration. And if we take half of that, it's going to be 1/16. And you get the idea. Basically, it's just dividing everything by half. And then what the half-life tells you is how long or how much time passes for half of that concentration to dissipate. Let's say our time is in days, right? Let's say our time is in days. So let's say the first half-life takes 8 days, right? And then the second half-life is going to take 16 days. Right, and our third half-life is going to take 24 days, right? So a half-life is just a measure of how long it takes for half of the reactant to dissipate over time. And that's pretty much it, guys. It's a really simple calculation. Let's go ahead and do a quick problem. Example questions that you might get on something like this would be like, for example, this is iodine, right? Let's say saying that the half-life of iodine is 8 days. What fraction of the initial iodine 131 would be present in a patient after 24 days if none of it were eliminated through body processes? Something like that, right? So basically we're looking at 24 days, how much or what fraction is left, right? So if U is left. So if you look at 24 days, right? 24 days is right here. So at 24 days, how many half-lives have happened over the course of 24 days? Well, that's 1, that's 2, that's 3 half-lives, right? So if you have a half-life, right? You have half-life 0, 1, 2, 3, right? The initial concentration at 0 is, of course, 1. At 2, it's 1/2. At 1, it's 1/2, 1/4, 1/8. So we just saw that it took 3 half-lives to get to 24 days, right? That's 3 half-lives of the original. So then the fraction would just be 1/8. It's, again, a simple concept to understand. If you have the rate constant for the reaction, right, then you would just plug it into this formula. And then your rate constant goes here. And this is for first order reactions. right? This is for first order reactions. For second order, it does change a little bit, but it's not much. Okay, for second order reactions, the half-life, and you may not even get questions like this, but I want to make sure that you go in there with all the information. It's going to depend on the initial concentration of the reactant. So it's pretty much the same thing, right? You're going to take the rate constant, right? And then you're just going to multiply it by the initial concentration. And that's going to be the formula that you use for half-life. But overall, very, very simple concepts. If you guys have any questions, please let me know.